Okay, so welcome to the last session of 4 weeks. So I'd like to introduce Thomas Blom, who's going to tell us about the chain rule in Goodwillie calculus.
Thank you very much. Thank you for the introduction, and thank you for organizing such a wonderful conference. It's such a great location. Yeah, so I'm going to talk about the chain rule in Goodwillie calculus. All of this project is joined with Max Blans from Utrecht University. So I will first start with something very classical, namely the Arone-Ching formula, and then I will jump from 200 years in time and go to Goodwillie calculus. If you don't know what Goodwillie calculus is, that's fine. I'll try to give an introduction, and then I will say something about what a chain rule in that context would look like, and yeah, state our main results. But let's start with the Arone-Ching formula. This is something very classical, and probably many of us have seen this a very long time ago. I never saw this in undergrad, but let's start with something we all saw in undergrad or even before, namely the chain rule. So the chain rule is, well, it's the following formula. It tells you how to compute the derivative of composite of two functions. And well, we all know it's very important. Then there's a somewhat related formula, the product rule, which tells you how to compute the derivative of the product of two functions. And one may wonder, is there also a chain rule for the higher derivatives? But as you can see, there's a product appearing in the chain rule. So if you want to iterate taking derivatives, then one has to combine these two rules. And if one does this and set up the induction in a clever way, then one arrives at the following formula. So the formula says that for the nth derivative, you can compute the derivative, the nth derivative of the composite of f and g, some large sum over partitions of n, and then, well, yeah, this formula. So I don't know how many people here are familiar with operands, but one might see that somehow there's some vague similarity between this formula and what is called the composition product of symmetric sequences. So keep that in the back of your mind.
So just to make sure, the bracket P means the number of terms in your partition.
Sorry.
Okay.
Yeah. So that's the cardinality of the set P, and then so that's the number of elements in the partition. Yeah. So yeah. But there are unordered partitions actually. So if you order them, then you need to start dividing out, and the formula becomes less clean.
And then the A inside the partition with the individual parts of the partition?
That's the individual parts of the partition, yes.
And why is it like why does it have A sides? Should it be So if we did go partition as a collection of subsets, there's a partition of a set.
Yeah, I think N as the n element set.
Okay, yeah.
Then B is a partition of n element set, so A is a subset of the n element set.
Okay.
So we can count its elements here. So, well, the question I want to answer today is how about a Arone-Ching formula in Goodwillie calculus? So let's start by talking about Goodwillie calculus, and because I think most people here are not familiar with it. So we saw in Catherine's talk that something about functor calculus and constructing towers of Taylor approximations of some sense to functors. So the idea, what we're going to do is we're going to categorify calculus in a way by categorifying the idea of Taylor approximation. But in order to make sense of this, we first need a notion of what it is, what a degree n polynomial is in our setting. So in our setting, it's going to be what it would originally called nxyc. So it's a functor that takes strongly co-Cartesian n plus 1 cubes to Cartesian n plus 1 cube. So I will define what this means by means of an example. So if we take n equals 1, then the strongly co-Cartesian n plus 1 cube is simply defined as a homotopy push-out square. So there's a homotopy push-out square, we can apply f to it, and a Cartesian two-dimensional cube is simply defined as a Cartesian square. So being one excisive is what people usually call just excisive. Namely, it's a functor that sends push-outs to pullbacks. It's a Mayer-Vittorius type thing, and it's F is some kind of homology theory in this setting. Then two excisive is going to involve three-dimensional cubes. And here I can actually illustrate what the definition of strongly co-Cartesian is. So this is a cube where all the two-dimensional faces are push-outs. So if we start with an object A and we have some maps with other objects, we can take push-outs, we can do it again. Well, it turns out that this always gives you the same object. And you get a cube like this where all the two-dimensional faces are push-outs. So such a cube is called strongly co-Cartesian. And then the condition is that if we apply F to this, then this is going to be Cartesian, meaning that the initial vertex of this diagram needs to be the limit of the rest of the diagram. So this red part is a cone from this diagram and needs to be a limiting cone. So that's what it means to be two excisive and while higher dimensional cubes gives higher notions of excisive. So there's a result that Goodwillie showed, namely that there's a way of approximating under certain conditions a functor by one that is n-excisive. So for this, I will give this is technical definition that you can forget after this slide, but I will just call a different infinity category differentiable if it satisfies presentability, which is just from the set here, the smallness condition. If it has an object that is both terminal and initial, meaning that's called pointed, and if filtered homotopy colimits commute with finite homotopy limits. And Goodwillie showed, well, not in this language, but he gave a proof that works in this setting that shows that if we are given two differentiable categories, then the inclusion of the n-excisive functors into all functors from C to D, this admits a left adjoint Bn. And so this is how he defines the n-excited approximation.
Can you give us an example of a differentiable category?
Yes, there will be some examples later, but the main examples to keep in mind is the category of pointed spaces and the category of spectrum. And then those are the main examples in this talk, at least. So one can show that a functor that is n-excisive is also n+1 excisive. So this means that by this left adjoint universal property, we're going to get a tower like this of approximations to our functor. So this is our categorification of the Taylor series of F. And one thing we can do is, if we're given a tower, then well, what do? We usually look at the layers and associated gradient and try to study that, and hopefully we'll get some understanding of the tower, and even better, if we can show some type of convergence of the tower, then we'll get a conditionally convergent spectral sequence and we can really start computing stuff. But for this, we need to understand the layers. So these layers are, one can think of them as the differences between the nth stage and the n-1st stage of the Taylor series, which is, so this, they are some kind of monomials. And they are what is called, they are so-called n-homogeneous functors, meaning that somehow they're concentrated in one degree. So the derivatives are defined in terms of these n-homogeneous approximations. So Goodwillie showed, and then well, in this language, some work of Lurie was also involved, that if we have a functor between differentiable categories that preserves filtered colimits, meaning it's finitary and the terminal object, then these derivatives, they admit some simple description in terms of certain things that we'll call derivatives. So these derivatives, they are functors from spectrum objects in C, so the stabilization of C, to spectrum objects in D of n different variables and that are symmetric in variables. So there's this h sigma n there that's some kind of orbit saying that this functor needs to be symmetric in the variables. And it preserves coordinates in each variable separately. And then there's some formula like this to reconstruct the layer from that information. And this thing is what we're going to call the derivative of f. And for those who are familiar with Goodwillie's work, so this is not how we stated the result, obviously. But one can show that if C or D are the categories of pointed spaces or spectra, then such a functor, this derivative type of functor, is completely determined by just plugging in the sphere and just evaluating it there. And then it's going to output some spectrum with a sigma n action. And that is something that you can really think of as the derivative, or like the coefficient of the n monomial in the Taylor series. Let's see. So let's do some examples before I continue. So first example is going to be of a linear functor. Linear means one-excited and that it preserves the one-point space. So if we look at the identity on spectra, then being linear or being one-excited means sending push-out squares to pull-back squares. Well, in spectra, these are the same. So it's going to be linear. And this is going to tell you that the first derivative is going to be, in this case, the sphere, which is the unit, and the other ones are going to be trivial. But then if we go to pointed spaces, that's somehow where things start to get a bit weird, because by saying that we want push-out squares to be sent to pull-back squares, we're in some sense saying that we're using a different type of additive structure on the source and on the target. And this is going to lead to the fact that the identity is not actually going to be a linear functor, but it's going to have higher derivatives, and one can explicitly compute what these are, and it's going to be the direct sum of a bunch of copies of shapes of spheres, where sigma n acts in some non-trivial way. And finally, to give one example that's not the identity, if we take some pointed Sidonia complex with a base point, then we could look at pointed maps from that thing into other pointed spaces and take the suspension of this. And turns out that the whole Goodwillie tower in this case can be computed by work of Arone. And the derivatives in particular are given by one smashes k with itself n times, then one divides out the so-called fat diagonal, and then one takes the spanier right into all this. Okay, now let's discuss the chain rule in Goodwillie calculus. So the chain rule, like in classical calculus, the chain rule tells you how to find the derivatives of a composite by studying the derivatives of the individual functors. And then somehow it tells you that you can reconstruct the derivatives of the composite by just from the derivatives of the individual functors. And so one thing one might try is that one starts like with the Fadi-Plummet formula, prove the chain rule for the first derivatives, prove a product rule, and then start doing some induction. But this type of induction where one computes the nth derivative or iterating this construction of just taking the derivative n times, this doesn't really work in Goodwillie calculus because it's not going to tell you what the sigma n action, like what the symmetry is on the derivative. So that's, you can't really recover that. So you need to do something more intricate. So let's start by just somehow, because the packaging all the derivatives into one mathematical object, because like the nth derivative of the composite in this Fadi-Plummet formula, it depends on also the lower derivative. So we should view them as one object. So I will call functor symmetric sequence from C to D just a category of such sequences where the nth functor is a functor of n variables from C to D that is symmetric in variables. So by what I said about the derivatives, one can somehow, so the derivative takes a finitely reduced functor and outputs all these different functors of many variables. So we can package this into one functor between these two categories. And then one can show that this category of symmetric sequences from C to itself actually admits a certain monoidal structure, which we'll call the composition product, and which is informally given by this formula here. And this starts to look, well, awkwardly similar to the Fanny-Bruno's formula. And for those who are familiar with the theory of operands and the usual symmetric sequences, if for C one takes the category of spectra, then such a symmetric sequence, functor symmetric sequences, again, you can evaluate it in spheres and it's completely determined by this. So in this case, you will just get the usual category of symmetric sequences in spectra, where you don't have anything in degree 0. And it turns out that this is exactly the usual composition product.
Maybe something. What do you mean by H sigma n on C again?
So this is, what I mean by this is you see the C as C to the power n as a category on which sigma n acts by permuting the different copies of C, and it's you take the homotopy orbits.
The homotopy orbits.
Yeah, so it's not a strict orbit. So instead of just taking the actual strict, yeah, I mean even with ordinary categories you can do it. So the idea is that instead of taking actual orbits, you glue in isomorphisms.
Right. Okay.
And those are the isomorphisms that somehow capture the symmetry of the object. So then in the stable setting, there's a result of first proof by Ching and then with a different proof by Arone-Ching later, namely that if we have two functors that are finitely reduced, then there's an equivalence like this. So this is a nice way of stating the Fanny-Bruno formula in this case. And under this equivalence between these functor symmetric sequences that I mentioned and the actual symmetric sequences in spectra, this really becomes the Fanny-Bruno type formula. So they conjectured that such a formula should hold much more generally, so that one should be able to replace spectra by any like stable model category or stable infinity category, maybe with a few assumptions, but that this they conjectured that this shouldn't be something specific to spectrum. And they also suspected that like this somehow this equivalence that they get should be part of an actual strong monoidal structure of derivatives. So where you also have the associativity covariances, things like that. So, well, that is the first thing that we proved. So we showed that if we have a stable infinity category that's also differentiable and is older sent from a few slides back, then indeed one can show that these derivatives become a strong monoidal functor. And in particular, that one also has like a Fanny-Bruno formula for the derivatives. And one thing that one gets from this, for example, is that like compared to the old result, our result, so it encodes certain coherences when it comes to the associativity. And what this gives you, for example, is that any monad or comonad in spectra, its derivatives are going to be operant or co-operant. One example here would be if you take the three algebras over some operand, this defines a monad in spectra, taking derivative recovers that operand. Something more to show. But then unstably is, well, we already saw that the derivatives of identity are not trivial. It's not a linear functor. So this already tells you that it's like a similar kind of Bruno style formula cannot hold. because, well, any strong monoidal functor would preserve the units, and in particular one would have an equivalence like this, but one can just check by hand that such an equivalence doesn't exist. But there's a way of correcting for this type of failure, namely by using relative tensor products, or in this case, a relative composition product. So this is where you try to divide out the action of this derivatives of the identity when you do the composition product. So how this is usually done is by using a certain bar construction, some of the derived version of a co-equalizer. And then, I mean, the formula is public, but ignore that. But the idea is that if S has a right action from something and T has a left action, then you can form such a bar construction and define a relative composition product. And what Arone-Ching showed in the case of pointed spaces is that like this first failure of namely the failure of the derivatives of the identity to be the unit, this is the only thing that is stopping you from having a chain rule. So if you mod out by so what they show is that the derivatives of the identity admits some algebra structure. And for any function pointed spaces to itself, their derivatives are bimodal, and you can form this relative composition product, and this actually recovers the derivatives of the composite. So based on this, you could ask for similar conjectures before. What if you replace pointed spaces by other categories, and somehow can this equivalence be made coherent in any way, such that you get a more structured statement? So this is what we proved in this case. So we don't obtain a strong monoidal functor because of this failure of the derivatives of the identity to be trivial, but we show that in general, if one obtains a Lax-monoidal functor, so the derivatives can be made into a Lax-monoidal functor with respect to composition of functors on one hand side and the composition product on the other side. And there's a canonical map. So if one has this structure, then one always gets a canonical map from this relative composition product to the derivatives of the actual composite, and this is always an equivalence. So this generalizes the result of Arone-Ching, and this was originally conjectured by Arone-Ching when they proved their results that there's such a general statement involved. And later, Lurie made this conjecture more precise in the language of infinity categories and made quite some progress on it but in the end, he had to state it as a conjecture in algebra. So I'm not going to say much about the proof because I don't really have time for that, and I don't think it will be particularly enlightening. But one feature that I think is nice to mention is that, like in the original proof by Arone-Ching, the idea is to somehow use some form of causal duality, show that it interacts really well with Goodwillie calculus, and that it allows you to somehow deduce an unstable chain rule from the state of mind. And something that one in particular obtains is this equivalence here in the derivatives of identity are somehow causal dual to the derivatives of the loop's suspension comonad. Finally, I would like to mention, so far I've only talked about functors from the category to itself, but in general, you want to study functors between different categories. So in order to actually do this and make this precise, we actually work with infinity 2 categories, and because then one can somehow package all these functor categories for different C's and D's into one big object, and we show statements at that level. well, that's what I wanted to say about this. So thank you for listening.
If I take the full model structure on category small categories, do I get a differentiable infinity category?
So I think, well, I mean, it's not pointed, but of course you can work with some kind of pointed categories and then it's fine. And then it is differentiable, but its Goodwillie calculus is not going to be very interesting, right? It's a very degenerate thing, but if you do this for infinity categories, then one does get something. But I think that the type of calculus that you'll obtain is somehow, if you take suspensions, which are like the main example of the push-out you see, Goodwillie calculus, this somehow kills all the category theory. You end up with something where everything is in variables, and basically end up with a space. So I think if you want to have an interesting calculus there, one somehow needs to really incorporate the two category theory that one has and maybe use some COCOMA constructions instead of push-outs. So I don't have any specific idea about this.
Any other questions? So, is there or will there be a situation where people looking at situation where you have a composition of functors and you can actually get something more specific information about the composition?
Yeah, so there's so one thing that we are looking at right now is one very interesting composition that one can take as a function from pointed spaces to itself is one can look at first one takes the nth suspension in the nth loop space, then suspension infinity and then loops infinity. So snake splitting is going to tell you that the derivatives of this are going to be the non-unital EM operand. But the chain rule also tells you that this is some relative composition product of the unit, some shifted Lie operand and over some shifted Lie operand. And so this gives a purely combinatorial description of what at least the non-unital stabilized EN operand is. So somehow it tells you that there's a completely combinatorial description of this very geometric object. So this is something that we're looking at because this should be related to there are these higher enveloping algebras that Ben Knudsen has written about, and it should be related to this. So because this allows you to write down a map, it allows you to write down a map from some shift of the D operand to the non-unital EN operand. And somehow this should be the map that controls the EN version of enveloping algebras. But I mean, this is all work in progress. Like we don't know yet if the map we obtain is a map of operands, for example. And another thing that I think one should be able, well, no, I shouldn't say that. One thing I hope that one might be able to show is that because causal duality plays such an important role, it seems to suggest that maybe there's a way of proving the causal self-duality of EN using Goodwillie calculus. That is something that we hope to explore. I hope that's somewhat satisfying.
Oh yeah, I'm very satisfied. Any question? Well, let's go. Thanks, Thomas, again.